Okay, we are on chapter 4, and last time we got into the atom, and we talked about chemistry stuff here, I think. So we talked about really some of the important sort of experiments that helped us understand sort of the structure of the atom. Remember, there's really several sort of things that occurred, including some experiments that dealt with electrons, which are negatively charged, protons, which are positively charged, and also neutrons, which really have kind of no charge. And there was sort of an early version of the atom, which was the plum pudding model, which was really sort of later found to be incorrect based on Rutherford's experiment with the gold foil. And ultimately, what was sort of determined was we had an atom that was mostly empty space. It had a very dense positive core, which is our nucleus, and found later on and stuff that in the nucleus we had our protons, which again are positively charged. We had our neutrons in 1930, which have no charge. And really, in that sort of empty space is really where we find our electrons. And our electrons are really flying around in that sort of empty space outside of the nucleus. There is an attraction between the nucleus, which is ultimately positively charged, and electrons, which are negatively charged. Remember, opposites attract. And remember that, as we talked about, electrons really do travel pretty randomly about that empty space. They do not travel in orbits, as we'll talk about. They don't travel in these pretty circles, but they do travel around in that space. Most of the mass of the atom is the nucleus, and that is because in the nucleus we have both our protons and our neutrons. And out of those three particles, the neutron is the heaviest, and the electron is the lightest of those guys. And the proton is super close in terms of mass to a neutron, but the neutron just barely beats it out. So it is the heaviest. But either one of these guys, the proton or the neutron, is about 1,800 or so times heavier than any electron flying around. So again, that sort of led sort of evidence that the nucleus is really the most massive part of the atom, because again, each proton and each neutron is significantly heavier than any electron that's flying around in that atom. Any questions on any of that there? All right, then we left off, I think, right here, I think. We're going to talk about some properties of atoms, which are the atomic number, mass number, and isotopes. And the chemistry of atoms really does come from electrons. They are really what is involved in all types of bonding, ionic bonding that we'll talk about, covalent bonding. It's really the electrons. If you just think about sort of the organization of the atom, electrons are on the outside flying around, right? So when two atoms come together, electrons are pretty much going to be the first people to say hello to each other as they're flying around. And really the only thing that happens, again, in a chemical reaction is we only break bonds and then we make new bonds. And that is all electron based. We actually never really in a chemical reaction touch any of those particles that are in the nucleus, like protons or neutrons. So everything, in a chemical reaction is all about those breaking bonds and making bonds and those electrons. And as we'll talk about, that's also why, for example, we have the law of conservation of mass and conservation of elements, because we don't really do anything with the nucleus, so we never really change elements in a chemical reaction. The only thing is we just kind of rearrange them into new compounds on the other side by breaking bonds and making new bonds. So the first important number is the atomic number. The atomic number is sometimes abbreviated as a Z, and the Z represents the atomic number. The definition of the atomic number is the number of protons you have in an atom. Now, if you have something that is neutral, since an atom basically only contains three types of particles, protons, which are positive, electrons, which are negative, and neutrons that have no charge. If you have something that is neutral, that means you need an overall charge of 0. So the number of protons would equal the number of electrons if you're dealing with something neutral. All the positive protons would be balanced out by all the negative electrons. It gives you no charge overall. We can find our atomic number by looking at the periodic table. And typically speaking, on the periodic table, it is the number above the symbol when you look at it. So if you look at hydrogen here, hydrogen would then have basically one proton, which is positive. And because it is no charge and nothing is written there, it would also have to have a matching number of electrons. Again, one positive guy, one negative guy gives you no charge overall. They basically cancel each other out in that particular case. If you look at the periodic table, or if you have a periodic table at your desk that you look at, you will see that every element on the periodic table has its own unique atomic number. So the atomic number, which is the definition of protons, or how many protons something has, every element has its own unique atomic number. Now, what that means is if you think about what is really the most important out of protons, electrons, and neutrons in terms of what element it is, which one would be most important? If the atomic number is the number of protons and everybody has a different atomic number, which one would tell you what element you're dealing with then? The protons, yeah. So the number of protons, or the atomic number, is the most important out of all three of those particles in an atom, because the number of protons you have, which is its atomic number, will tell you what element you have. So for example, if I have one proton, I know it's hydrogen, right? If I have 7 protons, I know that is number 7 on the periodic table, which is our friend nitrogen. So he's got 7 protons. He would also have 7 electrons if he was neutral. So every element has a different number of protons, and you will never find, for example, carbon with 7 protons, because carbon has 6, right? So 6 would be carbon. So if you know the number of protons or you know the atomic number, all you need is a periodic table, and you know exactly what element you're dealing with. Just got to go find that number and see what the symbol is and what it is, and you can do that. That is also why, for example, when we do a chemical reaction and it's only electrons involved, we never touch the protons. That's why we never change the element, because nothing gets changed in the nucleus. No protons get changed in a normal chemical reaction. So if you started with 4 carbons, because you're not going to touch any of those protons in each of those, you will end up with 4 carbons on the other side. Again, that's why we have the conservation of mass. Now, it is also really important, sometimes people mess this up, which is if you are asked the definition of the atomic number, the definition is just the protons, right? So it has nothing to do with electrons. It is just the protons. The thing that it tells you is, again, as we talked about, if it happens to be neutral, it'll also tell you the number of electrons. But if you're asked straight up a question, what is the definition of atomic number? It is only the number of protons. And again, you can find it on the periodic table. Any questions on that there? Another really important number is the mass number, and the mass number is sometimes abbreviated with an A, and that is the number of protons and the number of neutrons that you find in an atom. Now, the mass number is our number of protons plus our number of neutrons, and that's really important because if we take the mass number and the atomic number, which, as we just talked about, is the number of protons, and we simply subtract those two, protons go away, and that will tell you the number of neutrons there are in an atom. So if you take the mass number minus the atomic number, that will tell you how many neutrons there are in an atom. When you calculate those things, and by the way, everybody has protons, electrons, and neutrons. The only exception is hydrogen. Hydrogen actually only has a proton and an electron. It does not have a neutron, so it's the only element that doesn't have a neutron, but everybody else will have all 3. But when you do calculate all those things, if you're asked to calculate the number of protons, number of electrons, number of neutrons, the mass number, and the atomic number, Those things all should be positive whole numbers. So they all should be positive whole numbers. So that brings me to the next question, which is, I know that's my atomic number, right? And I look on the periodic table and I see something like that underneath hydrogen. Is that the mass number? That is not the mass number. And the way you can remember that is if you look at all the numbers on the periodic table underneath the symbols, they're pretty much all decimal point type numbers. And when you calculate mass number, atomic number, protons, electrons, neutrons, they all have to be whole numbers. So they are not on that. That's something we're going to talk about shortly. That is the atomic mass and not the mass number. So the mass number cannot be found on the periodic table. You do have to calculate it. You'll have enough information to calculate it in a problem, and also the number of neutrons. You'll have enough information to be able to calculate those if you need to, but it is not. Why people get confused sometimes is a lot of times, sometimes the mass number for a particular isotope is very similar to that number that you see on the periodic table. So people think, oh, they must have just like rounded or something, you know, to get to that number. So again, the only number you can find on the periodic table is the atomic number. Mass number you need to probably calculate if it's not given to you, and you will have enough information to do so. Any questions on that there? All right. Now, in most cases, and one of the things that we saw, atoms of a given element do not have the same mass, and that is what isotopes are. So that's one of the things that Dalton's atomic theory was incorrect about. The existence of isotopes are the same element, but they have different masses. Now, in order for them to be the same element, as we just talked about, the protons, electrons, or neutrons, which ones have to be the same for sure? If they're the same element, got to be the protons, right? Because everybody has their own. So what isotopes are things that have the same protons. And since the electrons are not very massive, right? They're the smallest, lightest of all of them. They actually have different numbers of neutrons, and that's what gives them different characteristics or different masses. So one way that we write sort of symbols for isotopes, we put the mass number upper left of the symbol, the atomic number on the bottom left there of the symbol. So for example, if we have hydrogen, which is obviously our hydrogen element, we have deuterium, which is sometimes referred to as heavy hydrogen, and tritium, which is the radioactive version of hydrogen. And we wanted to write the symbols for this guy correctly. The first thing we would do is we see we have one proton. If you by some chance wasn't sure what element it was, you go to periodic table and find number one, and you can see, oh, one proton is hydrogen, and that would be your symbol. The atomic number would be 1 in this case, bottom left here. Now, our mass number is the number of protons and neutrons. So in this case, 1 plus 0 is not 0, but it is 1. And we'll put that up on top. And that would be our mass number here. If you take the top number minus the bottom number on the left there, that will give you the number of neutrons. So 1 minus 1 is 0 neutrons in this case. So that is how you can get the number of neutrons. Now, let's just say you came across this guy, deuterium, and you're like, doesn't sound like anything I know. But what you see, you have one proton. All you have to do is go to periodic table and go, oh, this must be a weird name for hydrogen because it ultimately is still hydrogen. And that would be the symbol that you would use. It still has an atomic number of 1. But in this case, this guy has 1 proton and 1 neutron, which means the mass number here is going to be 2, our mass number. And that would go up on top. Again, 2 minus 1 is 1 neutron that deuterium has. Lastly, tritium doesn't really sound like hydrogen, but I know it's hydrogen because it has, again, 1 proton. And again, if I go to periodic table, that's going to give me hydrogen. And in this case here, 1 plus 2 is 3. And we'll go 3 for our mass number. So those are the 3 symbols for hydrogen, deuterium, and tritium. They're all basically hydrogen. They're all what are known as isotopes because they all have 1 proton. They're all the same element. They all have different masses because they have different numbers of neutrons. Any questions on that there? Okay, so that's a very common way that we write it. Another very common way that sometimes you'll see isotopes written is something like this. For example, Cu64. So if you had to take a guess, the 64 is what number you think? So let's take a look. If we go to the periodic table and we find copper, above copper should say 29. And we know that 29 is what number? That's the atomic number, right? Which is our number of protons. So we know that that definitely is not our atomic number. So that's most likely going to be our mass number. So that's your mass number. And if we were to sort of write it like the other form, we would take copper and on the bottom would go 29. Up on top would go 64. That would mean in this case, this, I can say carbon, but this copper atom here has how many protons this copper atom? Has 29 protons, right? Positive guys from its atomic number. This has no charge. And again, a reminder that if you're not sure if it did or not, there would be something written right about there if it did have a charge. So if you do not see anything, you could assume that it is neutral. And because it's neutral, then how many electrons should it have? Should also have 29 to balance it out. If you take all 29 positive things and add it to 29 negative things, that is no charge overall, right? It's all neutral. Now, the number of neutrons in this case would be our mass number, which is 64, minus our atomic number, which is 29, 34 neutrons in this case. Yeah. Any questions on how we got any of those there? Is it 35? I like it. I probably typed the wrong number in there. I did 35. Thank you. It's like 34, but I mean, I lost something along the way. These things, those neutrons, man, they fly off sometimes, So any questions on it? Thank you. Any questions? All right. Then let us why don't you try some here? So for each of these, let's do protons, electrons, and neutrons. If you have a periodic table, it'll be helpful. Just in case you don't, this is what cobalt looks like, chlorine, and uranium there. Okay, let's take a look and see. So once again, when we see it written like this isotope top number is our mass number. And again, that's our number of protons plus our number of neutrons. Bottom number is our atomic number. And that's our number of protons. So right off the bat here, number of protons here for cobalt should be 27. Again, it does not have any charge written there, so we could assume that it's neutral. So again, since these are essentially positively charged, it then needs to have a matching number of electrons to balance it out. Once again, 27 positive guys with 27 negative guys is going to give us a neutral overall sort of charge. For our number of neutrons in this case, we're going to take the top number, which is our mass number, minus the bottom number, which is our atomic number. And I'm going to try to do better than I did last time. 33, we'll go with that one there, hopefully. Yeah. Any questions on that there? All right, so Cl is chlorine. So once again, we know this bottom numbers are protons. So our number of protons here are going to be 17. Once again, no charge, so that makes it pretty straightforward. We should have a matching number of electrons to zero out our overall charge here. And again, our number of neutrons is going to take our top number, which is our mass number, which is 37 in this case. Let's subtract 17, and we'll go 20 on that one there. Any questions on that one? Lastly, uranium, they say. Also neutral, nothing written there. So starting with the atomic number of protons is going to be 92. Again, no charge, so matching number of electrons giving us no charge overall. And our number of neutrons in this case, 238 minus 92. Seems like a lot, like $1.46 there, I think, right? 146 neutrons in this case. Any questions on any of those there? All right, so let's try a few more here. Let's write the symbols. That includes the mass number and the atomic number for each of these. And again, in case you don't have a periodic table handy, let me write kind of what it looks like up there. So that's krypton, nitrogen is 7. And what we got there, iron there is 26. All right, so mass number, atomic number, and symbol, and then protons, electrons, and neutrons for the last one as well. Okay, let's take a look. So again, krypton here, we definitely want to go to periodic table to help us out. We got our symbol. And also from the periodic table, we could get our atomic number, which should go, again, bottom left of our symbol. In addition, that's also going to provide us a useful piece of information because that should tell us our number of protons is 36. And that's helpful because we need to also calculate our mass number, which is our number of protons plus our number of neutrons. So now we know we go 36 plus what they gave us, which was 48 neutrons in this case. And that's going to give us 84 here for our mass number. Yeah. Any questions on that there? Good. Yeah. Same thing here. If you're not sure, nitrogen is number 7 on the periodic table there. So once again, important information that we could get off of there is the atomic number and the symbol if you weren't sure. And again, that atomic number is going to tell us the number of protons, which is 7. Remember that the number on the bottom is not the mass number. So again, we want to calculate the mass number. So don't be the person that writes the decimal number on your exam. Yeah. So we're going to go 7 plus 6, which is our protons and our neutrons that was given to us. And that's going to be, we got there 13, I think. And we can go 13 up on top. Any questions on that one there? Lastly here, iron has a mass number of 56. So they actually gave us the mass number in this case. We would still perhaps need to go to the periodic table there to get our atomic number and maybe the symbol if you weren't sure. So that's going to be 26. They did give us 56. That atomic number is going to tell us that the number of protons here is going to be 26. It didn't mention anything about a charge, so we could probably safely assume that it's neutral, which means it should have an equal number of electrons in this case, giving us no charge. And lastly here, taking our neutrons, which is our mass number of 56, minus our atomic number of 26 gives us 30 for our neutrons. Any questions on how to figure out protons, electrons, neutrons, atomic number, mass number, all whole numbers, as you can see? Yes. Any questions? What happens if, while we have this page, what happens if something did have a charge, for example? So let's just talk a little bit about if something did have a charge, and maybe we'll just steal 2 on this page to look at that. I'll just steal these 2, I think. So if something has a charge, as we'll learn coming up pretty soon, and we'll learn right now, if something does have a charge, that is what's known as an ion. So ions are things that have charges. And there's 2 types of ions that we come across. There are things that are known as cations, and cations are positively charged ions. And there are anions, which are negatively charged ions. So let's just take, for example, our nitrogen here. And let's say we have the same setup here, 13, 7. But instead of it being neutral, let's just say it had a -3 charge, for example, right? So now if we want to know number of protons, electrons, and neutrons, we need to kind of figure it out perhaps. Number of protons here is still 7, right? And again, it cannot change because if I change the number of protons, will it still be nitrogen? No. So clearly we can't touch the protons, otherwise it's a different element. Neutrons have no charge, so they can't affect the charge. So that leaves, I'll use the right finger there, that leaves electrons there, right, as the only thing that can affect the charge. And that's what happens to give somebody a charge, positive or negative, is the electrons that change. So in this particular case, instead of 7 electrons like we have here in this example, it actually will have 10 electrons. Yeah. And if you take 10 negative things and you add 7 positive things to it, you are left over with a -3 charge. And that is where the charge comes from on the nitrogen. It basically has actually, if we look at the neutral one over here, this guy had 7 electrons. And the guy with the +3 charge had 10 electrons. The one with the -3 charge, did it lose or gain electrons from the neutral? It gained electrons, right? Neutral had 7. This guy with a -3 charge has 10. So it actually gained electrons. And that is what is known as an anion. These are things that gain electrons. And that's really what the charge tells you. When you see a negative charge, it means that it has gained electrons from the neutral. And the 3 is actually how many electrons it gained, right? So the 3 is actually how many it did, because the neutral guy had 7, it gained 3. 7 and 3 is 10 total electrons in this case. Any questions on that one there? Now, if we take iron over here, and again, we kind of roll, by the way, this guy would still have, in terms of neutrons, going this way, backwards, there we go. I would still have your 6 neutrons, right? Taking 13 minus 7 would get you your neutrons. We take this guy here, 56 and 26, and make it a +2 charge in this case. Now, when we look at it, once again, the number of protons here does still need to be 26. Otherwise, it is not going to be iron. The number of neutrons here is still the same, 56 minus 26, which is 30. So once again, here is the electrons that actually change when this thing gains a charge. How many electrons should this guy have? 24 electrons. Perfect. So if I take 26 positive things and subtract 24 negative things, that leaves me a net 2 + 2 charge. And again, that is where the +2 charge comes from. Those with a positive charge are known as cations. And if you compare the number of electrons here in the guy with the charge to the number of electrons in the neutral guy, it actually lost electrons. And that is what the charge indicates. If you see a positive charge, it means something has lost electrons, and the number is how many electrons it lost. So in this case, when we see a +2, it has lost 2 electrons from its neutral state. And that is how we get to that positive charge. Question on that. So if something does have a charge, once again, protons cannot be changed, otherwise you change the element. Neutrons have no charge, so they have no effect. So it's all about the electrons. Either they will gain electrons or lose electrons. And again, if you see negative charge, they've gained. Positive charge, they have lost. And the number tells you how many you need to add. So essentially, you could use the atomic number and the charge to help you figure out the electrons. So for example, what I'm saying is nitrogen's atomic number is 7. And when I see a -3, that means it gained 3. So I need to add 7 and 3 added together is 10, right? If I look at iron, iron's atomic number is 26. +2 means it's lost 2. So 26 minus 2 is 24 electrons. So you can just kind of do it that way if you want. And that is how you can figure out the charge. Any questions on things with charges and what affects it? No? Okay. All right. Hopefully they agree. There we go. So as I mentioned before, isotopes are really determined by the number of neutrons. And under normal conditions, the good thing is, as we've been talking about, protons and neutrons and stuff in the nucleus really don't participate. It's all about electrons. So one of the nice things about isotopes, for example, is you could use a radioactive version of an isotope. And if you're interested maybe in, like, say, what's going on with copper, you could use a radioactive version of copper. It will do the same chemistry as a non-radioactive version of copper, say in the body or whatever it may be. And you can follow the radioactivity to see, like, where it goes. Say if you're doing protein purification or something like that that involves copper, you could kind of do that and follow exactly where the copper goes. It will do the same thing as kind of the non-radioactive version of it. So it's used a lot in laboratories to kind of do those type of things. So let's talk a little bit about chemical composition. And now we're going to talk about really the number that's on the bottom of the periodic table there underneath the symbols. And those are atomic masses. And atomic masses are one of the fundamental properties of an atom is its mass. Obviously, atoms are super small, so you can't just like pick one up and pop it on a scale or anything like that. So typically speaking, in chemistry or in science in general, if you cannot, for example, directly measure, for example, an object, a lot of times what they will do is choose something as a standard, and they'll choose it as a standard to sort of compare everybody else to. And for atomic mass, they actually chose an isotope of carbon as the standard isotope. They chose the carbon-12 isotope. The carbon-12 isotope has a mass of what's known as 12 AMU, and that's an atomic mass unit. And that is just a unit of atomic weight or atomic mass as taken from the periodic table. So what they found, for example, is the hydrogen atom is only about 8.4% as big as the carbon-12 isotope. So let's do a simple sort of calculation of 0.084, which is basically 8.4% converted into a decimal times 12. And you get something like 1.008, which again is your number that you see there on the bottom of the periodic table for hydrogen. Simple calculations have been done for everybody on there. So for example, if you look at iron, you will see 5585, and you could actually pull that number off and use it as a conversion factor. You could say there is basically 55.85 AMU per atom, and that is one way you could use it. You could also flip it around if you needed to. An atom would have 55.85 AMU. Now, to be truthfully honest with you, AMU is a unit that is not super useful to us because, as you might know, if you go to your balance in the laboratory, they typically give you units of grams, right? And very commonly we weigh things in grams. So later on, we will use this number on the periodic table in a more usable unit, which is known as molar mass, and that's in grams per mole, and that will get us to grams, which is again a more usable type unit. But mathematically, as we'll talk about in that when we get there and talk about that, is the AMU per atom and grams per mole, they're the same number. So they end up being the same number through a conversion that's there. You can find the atomic mass of everybody on the periodic table, which once again is not the mass number, right? So again, not the mass number, but the atomic mass. Now, when you look at something like carbon on the periodic table, and you may say to yourself, carbon says 12.01 on the periodic table, but you just told me carbon-12 was the isotope that they use as a standard that has a mass of 12 AMU. And the reason for that is what we actually see on the periodic table is the average atomic mass, even though nobody really calls it average atomic mass, but it is the average atomic mass of all the naturally occurring isotopes for that particular element. So for example, carbon may have carbon-12 and also carbon-13 isotope that appears in different percentages. And it's the averaging of those two guys that give us the numbers that we see on the periodic table. Now, there is a calculation that you can do to calculate the atomic mass, and that is this calculation here, which is the atomic mass in AMU is equal to the percent abundance of the first isotope of that element times the atomic mass of the first isotope. Then you add it to the percent abundance of the second isotope times the atomic mass of the second isotope. And then you add it to the third isotope, fourth, or however many isotopes you got going on there for that particular one. Now, this is a plus in between each of those calculations. People always want to multiply for some reason. So it is actually adding between those two, not multiplying. The percent abundance, or sometimes referred to as percent relative abundance, is the percentage of how often that particular isotope occurs in nature. So for example, maybe you have two naturally occurring isotopes for an element, and maybe one of them occurs like 80% of the time, and the other one occurs about 20%. And that's what the percentage we're talking about there. Typically in problems, they'll give you that information like, hey, this one occurs 80%, this one maybe occurs 20% of the time, and that's how you do it. If you're going to do a math here, you do want to convert that percentage into a decimal. So you could do one of two things. You could either move the decimal place 2 places to the left, or you could divide the percentage by 100 and it will move it for you. But you do want to make sure that you do turn it into a decimal before you do the math part of the calculation. So for example here, if we take this here, which is carbon, this is our carbon-12 isotope, and this is the atomic mass of the carbon-12 isotope. And essentially it occurs about 99% of the time, basically. This is our carbon-13 isotope, and the mass of the carbon-13 isotope, as you can see, is a little bit different, and it occurs about 1% of the time. So if we were to do our calculation like you see on the bottom there, our atomic mass would equal, we would take our first percentage of our first isotope, and again, it's your call. You could go 98.97% divided by 100%, and that will turn it into a decimal, or you can move the decimal place. We're going to times it by the atomic mass of our first isotope, which is 12. Then we're going to add it to our second isotope, which occurs 0.11% of the time. And again, I'm just going to move the decimal on this one. So we'll just move it there, right? Percent. And we're going to times it by the mass of the second isotope, which is 13,003 AMU. And as you can see down here, if you do all that, there's our 12.01 that we get on the periodic table for the atomic mass of this particular isotope. By the way, when you do this, it's probably a really good idea to make sure that the percentages should add up to what number? About 100, yeah. So it may not be perfect, but it should definitely be like in the 100 ballpark. It could be a little bit over 100, maybe a little under 100. But if you add it up and you only got 70% of the isotopes there, you're clearly missing 30%, right, of some isotope or multiple isotopes. And if you had some situation like that, it probably would give you some information in the problem, obviously, to figure it out. But 100% is, you want to make sure. So obviously in this case, 99 about 1, right, is about 100%. So we have all the isotopes present. Any questions on that there? All right, so why don't you try one here? Bromine has 2 stable isotopes, bromine 79, which occurs about 50.70% of the time, and bromine 81, which occurs about 49.32% of the time. The atomic masses for each of them is 78.92 and 80.92 respectively. Determine what the atomic mass is for bromine. Okay, let's take a look. So again, we have 2 different isotopes given to us. We do have our percentages or relative abundance here. So if we take a look at our percentages and add them together, we are in that 100% range. So we're definitely not missing anything. So we got bromine here, 79. It occurs about 50.70% of the time and has a mass of 7892 AMU. We have bromine 81, which would be its mass number, right? And that occurs about 49.32% of the time and has an atomic mass about 80.92 AMU. So if we calculate our atomic mass here, We'll take our first isotope. And again, however you want to do the percentages, but you do need to get into a decimal. So in this one, I'm just going to move it 2 places to the left, and that will give me 0.5070. Once again, you could also divide it by 100, and it'll move it for you, whichever way you want to do it. I'm going to multiply that by 78.92 AMU. I part. Do the same thing for here, just to show you both ways. Again, you could go 49.32% and divide it by 100%. With a decimal for you if you rather do it that way. And again, you're going to multiply it by 80.90 AMU. And that's going to get us here. Hopefully one of those numbers on the screen, I hope. Let's see here, 78.92 plus 0.4932 times 80.92 there as well. Looks like 79.92 AMU in this case. Looks like D is the winner there, yeah. Question on that. Yeah. No, because they do occur at different percentages. So they're not 50-50, right? So because they do occur at different percentages, you do have to take those percentages into account. Yeah. Other question. So the average is really not an average of not necessarily an average of the atomic masses, but it's the average of the masses of all of them kind of together, naturally occurring ones. Now, it's also important to remember because these are average atomic masses, and that's about what we see on the periodic table for bromine. It's like 7990. I think if you look up there, it's pretty close to that. So, for example, like the carbon, which was 12.01, you would never, for example, if you could pick out a carbon atom, you would never find one that's actually has a mass of 12.01. You would find one that's either 12, which is the carbon 12, or 13 and change, which is 13, carbon 13 isotope. So you'll never really find one of that mass. It's just an averaging of all those naturally occurring isotopes. Any questions on that there? All right, speaking of the periodic table, let's officially talk about the periodic table. That is the periodic table. Good talk. So we've seen some things on here. Let's talk about a few things. First off, elements in a column on the periodic table, that's going up and down. That is called a group, or if you're really old like me, a family. Nobody calls it a family these days. They all roll with groups these days. And there's different numberings. If you look at the periodic table, maybe that one up there, this one here. There's typically sometimes 3 sets of numberings that you see up there on top. There is what is sometimes referred to as the A numbering, which is sometimes referred to as the representative numbering. There's also the B numbering, and then there's just a straight like 1 through 18 type numbering all the way across. Pretty much in most chemistry classes, pretty much all chemistry classes that you take, we basically use the A numbering, and that is what we number our groups. So with the A numbering, right here is technically group 1. And by the way, group 1 actually starts with lithium, not hydrogen, even though it's hanging out there. Right next door is group 2. And then we actually skip the whole middle section here, and we pick back up over here. This is group 3, group 4, group 5, group 6, 7, and group 8. So we do use the A numbering, and I would say most people don't go 1A, 2A, 3A. They just go group 1, group 2, group 3, and stuff like that. If you want to put the A in, there's not wrong with it, but that's usually what most people will use. So again, going up and down is a group. Going horizontal, so going up and down is group there. Going left to right there is a period on the periodic table. And there are 7 periods on the periodic table going in this direction. 1, 2, 3, 4, 5, 6, and 7. As we also talked about, our number there on top of the symbol is our atomic number, right? Which is our number of protons like we talked about earlier. So groups going up and down, periods going left to right on the periodic table. And again, obviously our atomic number. And as we just also talked about, number on the bottom there is the atomic mass. Again, not the mass number, right? Now, the periodic table is basically broken up into 3 sort of categories. There are metals, nonmetals, and metalloids. On most periodic tables, including that one up there, you usually will see some type of what is referred to as a staircase right around where boron's at. Coming this way, and I think they drew it on red on the one up there hanging. And to the left of the staircase, those are metals, and metals are good conductors of heat and electricity. They're usually very shiny in appearance. You can pull them with the wires. For the most part, all metals are solids at room temperature. The one exception is mercury, which is Hg. On a lot of periodic tables, mercury will actually be a different color, written in a different color, like blue in a lot of cases to indicate that. Mercury is a liquid. All other metals are solids at room temperature, or normal temperatures. To the right, upper right here of that staircase, going in this direction, we have our nonmetals, and they basically are the opposite sort of characteristics. They're dull, they're brittle, they're insulators, they're bad conductors of electricity. Now, we talked about a second ago, this is hydrogen, this is lithium, this is group 1. Why is hydrogen not part of group 1? Because hydrogen actually is but what type of element is it? Metal, non-metal? It's actually a non-metal, right? So hydrogen is actually a non-metal. Everybody else in group 1, metals, right? So that is why it's not there. It's hanging out in group 1 because it shares a lot of characteristics with members of group 1, and we oftentimes almost treat it like somebody in group 1, but it actually is a non-metal. And old time periodic tables would actually throw hydrogen sometimes on both sides. You'd actually see it hanging out on both sides of it. But nowadays, they usually just kind of keep it over there in group 1. But it actually is a non-metal. Again, that's why group 1 starts with lithium and not hydrogen because of that. Also, there's a much more variable type of states that those are in. Nitrogen, oxygen, chlorine, they're gases. Bromine's a liquid, a little bit of vapor. Carbon and sulfur are solids. Also, most of the nonmetals are our diatomic elements, like some of you mentioned. Hydrogen is hydrogen gas, right? Nitrogen gas, oxygen gas, fluorine, chlorine, bromine, and iodide, right? So those are all, again, as we talked about, I think earlier, those are all elements. They're diatomic molecules, and that's how naturally pretty much all these come, and they're all pretty much non-metals. By the way, also a reminder that things on the periodic table, again, do not have charges unless they hook up with somebody, right? So if you just have them by themselves, they are neutral and no charge. The staircase there, which some books include boron and some don't. I don't think yours does, but coming down here, oh, missed my staircase there. That is our metalloids. Those are also sometimes called semi-metals. These are elements that actually have characteristics that basically could fall either way from where they're sitting. So they have some characteristics that people would say that's very much like a metal characteristic, and the same element will have some characteristics that people would go that's very much like a non-metal would have. And that makes sense if you think about where they're located. We got metals transitioning into non-metals. So they're almost like a transition point between metals and non-metals. So they do have characteristics that sort of fall on both sides of the staircase along the way. By the way, the 2 rows on the bottom here, these guys are metals as well, and they go along with all these guys over here. Now, some groups do have special names that you do need to be aware of. So group 1, which once again starts with lithium, these are the alkali metals. So here's our alkali metals, group 1. Right next door in group number 2 is our alkaline earth metals. The word alkaline pretty much means basic. And group 1 and group 2 on the periodic table is where a lot of strong bases come from. If you hook those guys up with some hydroxide, OH, like sodium hydroxide, potassium hydroxide, calcium hydroxide, these are where a lot of our strong bases kind of come from, group 1 and group 2 on the periodic table. Specifically, if you kind of go this way and this way, hook those guys up with some OH, and you have some strong base basically formed. Coming all the way across there to group 7, those are our halogens. Those are, again, our fluorine, chlorine, bromine, and iodide. And right next door is group number 8. Those are our noble gases, and noble gases are chemically inert. What that means is they're very unreactive. They're extremely stable, and noble gases are really important, as we'll talk about in future chapters. They are essentially what everybody wants to be like, and that's really the whole reason for bonding, making ionic bonds, covalent bonding, all bonding is for everybody, as we'll talk about, to basically end up with the same type of electron configuration as the noble gases because they're super stable. And that's sort of the goal. Like everybody wants to get there in terms of their electrons that makes them really, really stable. The 2 rows at the bottom, like I mentioned before, are set aside so your periodic table is not too wide. But if you follow the actual numbering here, we got 57 and then 58. So this guy actually goes, that row goes right there. Then we have 89 and 90, and this guy goes actually in there. So those are where those guys should actually go. I've never really seen it done, only on one classroom I teach at, and it took up the whole wall because the entire periodic table has to be shifted to the right to put those guys in their proper place. But most of the time, they're just kind of thrown on the bottom. Good news in here, we really don't use too much of those guys on the bottom, except for uranium pops up occasionally in terms of names, stuff like that. In between group number 2 and group number 3 on the periodic table, these are our what are known as our transition metals. And one of the things that we'll learn very quickly about transition metals are they actually have the ability to make a variable type charge. So depending on the situation, you may have the same element, but it can make different charges. Like copper can make very commonly a +1 charge, and then in other situations, it can make a +2 charge. Our iron, for example, can in certain situations make a +3 charge, and in other situations make a +2 charge. So they oftentimes will have very variable type of things. That's also why the 2 bottom rows here that technically go in there, and by the way, they're called the lanthanides and actinides series because those are the elements they follow on the periodic table. Those guys are sometimes also referred to as inner transition metals because they kind of go in that sort of spot on the periodic table. Any questions on periodic table? So you need to know which way groups go. You need to know the group numbering. You need to know which way periods go. You need to know where you find the alkali metals, alkaline earth metals, the halogens, the noble gases, the transition metals, and obviously you need to know what things are metals, nonmetals, and metalloids. Any questions on any of that there? A reminder that your periodic table that you'll be provided on the exam will not have names on it, yeah, but we'll have symbols and everything else but the name, basically, yeah. And it won't have the titles up on top, like this is the alkali metals and stuff like that as well. All right, so now we're going to talk about really electrons and sort of what happens with electrons a little bit and electron configuration eventually. One of the things that happens with electrons in an atom, for example, is electrons are in different energy levels. And what can happen is if you excite in an atom, what you're actually going to be doing is exciting the electrons. And what can happen is electrons from, say, a lower energy level may find itself going to a higher energy level because it gains some energy. Now, what's going to happen in chemistry, and much like life, is we like to be in a low state of energy. So those electrons that go to the higher state of energy will eventually want to work their way back down, maybe to a lower state of energy. Conservation of energy tells us in order for them to come lower in energy from a higher spot is the atom itself will give off that energy, and the atom will give off that energy in the form of a wave or a photon of light. And that wave will have a specific wavelength that may fall somewhere on what is known, what we're looking at here, the electromagnetic spectrum. And the electromagnetic spectrum is where different wavelengths and different energy sort of comes together. Now, the relationship between a wave and energy and so forth, a wavelength is between 2 sort of peaks, is sometimes abbreviated with a lambda. That stands for wavelength. And if you have a long wavelength, You will also have what is referred to as a lower frequency, which is basically how many times that wave passes a point per second. And that usually results in low energy. And that is different than if you had a wave that had a much smaller wavelength like this. This wavelength is like between here. So this guy has a much shorter wavelength. That usually has a much higher frequency because it's just going to start flying really quick right through a point. And it will have much higher energy. So if we look at the electromagnetic spectrum here, and we look at the wavelength, what we have on, let's shrink this a little bit there, maybe. There it is. On this side, we have 10 to the 6, which is a much longer wavelength, as opposed to this side, which is 10 to the something there. Again, oh, I can't see that, but 10 to the minus 11 we'll go with, which is a much smaller wavelength. So when we look at this, we have much lower energy on this side and higher energy on this side. Now, so for example, on the left-hand side, we have power lines, we have radio waves, like you listen to the radio, right? When you turn your radio to a specific station, that is the frequency of that station, right? Like 95.5 megahertz is basically what the thing is, right? 102.7, right? All those things. Whatever you listen to, 94.7, the wave, whatever it may be. Those are your frequencies, and you're dialing that in. So wavelength has a longer radio waves have a longer wavelength, not as high as energy. If you kind of go to the right here, we then hit microwaves, which has a shorter wavelength than radio waves, has a little bit more energy, right? It has enough energy that you can throw your pizza into the microwave, right? It'll spin your water molecules really fast, and your pizza's done in 2 minutes, right? Good deal. And that's a little bit more energy associated with that. You go a little further to the right, our wavelength is getting smaller, and that's the infrared part of the spectrum. And that's usually where you feel heat from that part of the spectrum. If you go to the right, you have the visible part of the spectrum. That is everybody's favorite Roy, right? G, Biv, right? We'll go that way. IV. Red, orange, yellow, green, blue, indigo, violet. That's where we see color, right? So if waves are coming off at that wavelength, that's where we see actual color. To the right of that is UV, a little shorter wavelength, a little higher in energy. That's why we put sunblock on right when we go outside, so we don't get too burnt from the UV rays, right? It's beating down on us. X-rays to the right, a little much shorter wavelength, much higher energy. Also why they throw a lead vest on you typically, right? And they don't stay in the room with you when they shoot that X-ray, right? They usually leave the room and stuff like that to protect yourself, hopefully. And gamma rays, which we talked a little bit about when we talk about the atom, that's just pure energy, right? That is straight, just pure energy, super high energy. If you ever work with anything that's radioactive, that's a gamma emitter. You need to take some good precaution for yourself. So you do that. So what does this have to do with electrons? So as I mentioned before, as electrons, for example, transition from a higher energy level to a lower energy level, the energy given off by the atom could fall somewhere on this electromagnetic spectrum. If it falls in the visible part of the spectrum, you will actually see color, hence fireworks, right? Fireworks, they shoot it up, they exploded, right? Lots of energy when they do that. The different elements in those fireworks, right? Their electrons go crazy, they start relaxing, they give off energy at the visible part of the spectrum. We go cool, red, blue, green, all the colors that we see. You've probably even done it yourself. Maybe if you have a flame gas top stove and you boiled some water to make some noodles or some pasta for dinner and it overboiled, right? And water like hits the flame. Flame goes from like blue to orangey yellow really quick, right? You just excited the sodium in there, right? And that's what that yellow little flame actually becomes really quick, and then it goes away as it sort of goes off, and that's the visible part of the spectrum that you can see. And here again, just another representation of that. Even colors have different energies. So for example, red is a much lower energy color than, say, purple or violet. It's much higher in energy. So even in terms of colors, there's a difference in the energy. For example, if you're seeing some type of color as a result of electrons transferring from different energy levels and you see red, what that could tell you is maybe it did only transfer a very short period of energy, as opposed to if you see like a purple color, maybe it was a much longer energy transition that had to be given off by the atom. That kind of tells you those things. So we want to identify the electromagnetic radiation and which pair is greater. So again, these are our colors. So remember, red is lower in energy, right? And kind of the purple side there is a little higher in energy. So in this case, the one that should be greater in energy is blue light, right? So it should be blue. Ultraviolet or infrared, right? If you remember, ultraviolet was right there before X-rays, right? So that is, again, a much shorter wavelength, a much higher in energy. So ultraviolet. X-rays and microwaves, one you don't need the lead vest for, so I'm going to go with the X-ray. You might need it on that, hopefully, as we go through that. So you don't need to know exactly where any of these sort of break off in terms of numbers or anything like that, but you do need to maybe answer a question or so like this, put it in order in terms of energy or wavelength or something like that. So in terms of electromagnetic spectrum, that's sort of what you sort of needed to know from that. As I mentioned before, one of the sort of characteristics actually of elements as you excite elements in their gas phase is they will give off what is known as a atomic spectrum or an emission spectrum, and it's actually known as a line spectrum. And this is a line spectrum, and a line spectrum is much like it sounds like. You see distinct lines come off and they result from electrons transitioning from different energy levels. And that is different, for example, than what you see for something like the sun. If you're to, don't look at the sun, but if you were to see something that was lit by the sun, and you looked at it through a prism or a spectroscope, sometimes that you look at, and again, don't look at the sun, you will see more of everything coming off. And there's two types of energy that sort of happens. Things like the sun are what are referred to as a continuous spectrum. And that basically means that everything's coming off at once, basically. Things like atoms and elements in their gas phase, they are what are known as quantized energy. And quantized energy means only specific amounts of energy are being released, and they're based on the electrons transitioning. A very simple sort of explanation of quantized versus continuous is stairs, right? So stairs is a quantized energy. And what we mean by stairs is if you walk stairs, right? And this is kind of what you think about for electrons, and this is how electrons move in atoms. You will either be on this step, right? You will either be on this step or that step, and you have enough energy as you're going up or going down to make it from one step to the next, right? Most people do not decide halfway up this step, I'll just vacation right there and stop, right? Because you're going to fall, right? So you either have enough energy to kind of go up one step or down one step. You'll never stop in the middle. And that's the idea of what is known as quantized energy. Some people, by the way, could do two steps at a time, right? And same thing with electrons. They could go from like 2 energy levels up or 3 at a time, and they will have enough energy to fully do that transition. They'll never find themselves in between energy levels. And because of that, if you have an electron on the third energy level and one on the, and it comes down to the first, that's always going to be the same amount of energy required to do that. And when that's given off as a wave, that's going to correspond to an actual same color and wavelength of light, one of those lines that you actually see on the spectrum there, the orange line, the yellow line, whatever line it may be. Now, what a continuous spectrum is like everybody's coming out at once. You can think of that like a ramp. On a ramp, you could literally stop anywhere you want. You're going to be fine, right? And everything's coming out at once. There's no situation with that. And that's what things like the sun give off. They give a continuous spectrum of everything basically comes out at once, like white light. You got all the colors sort of coming out at once. But we get these very distinct line spectrums coming out for elements because we have these very distinct transitions of an electron who, if he's going to come down, he will lose enough energy to fully come down to that energy level, or maybe he'll come down to this energy level. But again, he will never find himself like stuck between energy levels. So he'll always make a full transition from one energy level to the next. And again, that's the staircase quantized energy approach. Now, Maybe you want to turn chat. There you go. Maybe turn. There we go. Now, when we talk about energy level and electrons transitioning from one energy level to the next, this is what is known as the principal quantum number. And the principal quantum number, there's actually 4 different types of quantum numbers, but for us, we're just going to talk about the principal quantum number. And the principal quantum number is n. And n basically is a fancy way of saying it's the energy level. And n could have values of 1 through 7. So there are 7 energy levels within an atom of where you can find electrons being housed. The n equals 1 is the ground state. It is the most stable. And it is closest to the nucleus. Anything that's above that, n2 through 7, are what are sometimes referred to as excited states. They are higher in energy, and they are further from the nucleus. So one of the things we think about when we think about where electrons are sort of found in the atom is they're either on these different energy levels, and there's 7 different ones. You can think of it like different floors at a hotel, right? You got to go to a certain floor to find your room, right? And in your room, there might be maybe have a suite and there's multiple rooms in there or something like that, right? So that's sort of the idea here of where in the atom in terms of energy we could find different electrons. And again, as I mentioned before, they are quantized energy levels. And that what that means is if an electron, for example, was up here on the 5th energy level, it would have to drop down fully to another one. Again, it would not stop in between energy levels. It will fully be able to make that transition downward and also upward, by the way. When it gains energy, it goes upward, and they fully go from one energy level to the next. They don't go in order, so not all electrons go like, I'm going to go from like the first one to the second one, the second one to the third. They go maybe from the first one all the way up to the 5th, right? And then maybe go from the 5th one all the way down to the 2nd. They won't stop in between. All right, so let's talk about what happens when you do gain energy for the atom. That's an endothermic process, and energy is absorbed. So as I was talking about, when energy is absorbed, you're going to find the electrons, for example, going from a lower energy level to a higher energy level, right? So when energy is absorbed by the atom, that's going to cause those electrons to basically jump up. It's kind of like what I was talking about when the water overboils. When the water overboils and actually hits the fire that's underneath it, that provides a heck of a lot of energy to those sodium atoms, and that's going to cause all those electrons to go to the higher energy level. And what's going to happen is, again, as I mentioned, if an electron kind of is at that higher energy level or gets up there, it will eventually work its way back down, and that is going to be energy given off by the atom, are sort of a exothermic type process. That's what happens, for example, neon lights, right? You turn on the power, it's electrical current going through the gas that's in your neon light, exciting all the electrons, and you see like the red color, green color, whatever colors of your neon lights that you may have. Like if you go to Vegas and all those things, they maybe still have neon lights over there in Vegas. Now, we have electrons on different energy levels. Where they're actually found in the atom is in these what are referred to as orbitals. And these are theoretical type of locations in an atom of where you can find an electron. So an orbital, any individual orbital could hold a maximum of 2 electrons. So any orbital on any level could hold a maximum of 2 electrons. Now, on the very first energy level, the only orbital that is there are what are known as s orbitals. And s orbitals look like you see here in the picture. It's basically a sphere. There's only one type. There's only one type of s orbital, no matter what energy level you're on. For example, if you're on the first energy level, it's known as a 1s orbital. If you go to the second energy level, it's known as a 2s orbital. If you're on the third energy level, it's a 3s orbital, and so forth. There are also p orbitals that look like these figure eights, and they start on the second energy level. So that's where they first start to appear. And there's actually 3 different types of p orbitals. There are what are known as the px orbital, the py orbital, and the pz orbital. If you think about math, the little Cartesian plane, x, y, and z axis, they're in 3 different ways in 3-dimensional space. There are also d orbitals, and they do not start until the third energy level. And there's actually 5 different types of d orbitals. And the last type of orbitals we come across don't begin until the 4th energy level. And there actually are 7 different types of f orbitals, which kind of look like what you see in the picture. Now, this is important because the total number of electrons, if you max out an s orbital on any level, because there's only one orbital can hold how many electrons? 2. So if you max out an s orbital on any level, you can only put 2 electrons in there. Now, because there are 3 different individual p orbitals, each one could hold 2, which means if you max out all of these guys on an energy level, how many electrons can you put in there? 6, yeah? Now, there are 5 different d orbitals. We assume these lines are the d orbitals. And if I max out all 5 of those d orbitals on any energy level, how many electrons could I put in there? 10. And there are 7 here, right? If I max out all 7 of those f orbitals on any level, I can max out with 14 electrons. And those numbers are really important, 2, 6, 10, 14. That is the maximum number of electrons that you can put in these type of orbitals on any energy level. By the way, we have a grouping of 3 different orbitals that are p orbitals on any energy level. On any energy level, there are d orbitals. There's a grouping of 5 different ones and 7 different ones. These are also sometimes referred to as subshells or sub-level, depending on your book. And that's a subshell or a sub-level. And that's a subshell or a sub-level. So that would be referred to as the p subshell, right? All 3 of those individual p orbitals together. This would be the d subshell, all 5 of the individual d orbitals together on energy level. And this would be the f subshell, all 7 of them on energy level. We do not refer to s orbitals as subshells because there's only one orbital on any energy level. So we just refer to it as a orbital. All right, we will lay it